Hello, I am Jim Potvin, and in this video, I'll introduce you to the Works web-based interface. So for starters, you would log in, and then you would come to this Works software page, and then you can click on Works software. So we're going to start from scratch. Once you have a report made, you can load it in here, and I'll show you how to do that at the end. So this is broken into a number of steps. For now, I'm just going to expand them all. So we'll have all the inputs at our disposal. So what we're going to do is, so we can pick between male and female mannequin, and you can see that the height. So this is just a visual representation of how things are going to look once you put in the results. So it just gives you some feedback to make sure that you're putting things in correctly. You can choose between metric and imperial. I'm going to use metric for this example. You can choose the DC, so the demand capacity ratio percentile. So that means that of all of the, let's say we generate 20,000 postures for this particular task, and we do an analysis on each of them for each variable as we went from, let's say, the lowest compression, the 0 percentile compression, up to the highest compression, the 100th percentile compression. We're going to cut that off at the 25th. You can set that, but we've established our best estimate of what that should be is the 25th percentile, because it's saying that a worker couldn't possibly do it in the best way every single time, and what's best for the back might not be best for the shoulders, etc. But a skilled worker is also probably not going to be in the upper ranges of risk very often. So we think this is a reasonable area to cut the risk values off. So you can pick from the body masses, and you'll see again, for body mass, you can pick one of 3 percentiles. And when you put that value in, you'll see, for example, what the 50th percentile female mass is. You can also go to a specific mass, and at that point, you could then enter the mass. So you might set that to 100 kilograms. But in this case, we're going to use the 50th percentile mass. So this option only comes open when you put in the specific mass. You can pick one of 3 statures, and again, these are shown graphically here, and the value is indicated. So we're going to use the 50th percentile female, and as is mostly the case, we're going to use a 75% capable, meaning that this task will be acceptable to all but the quote-unquote weakest female, 25th percentile female and lower, or 25th percentile male and lower, depending on what you pick. So the next thing you can do is determine the type of task that they're doing. So when we say standing, the static exertions can either be done standing. Most of the analyses will probably be done this way. We can have seated work. We can have a sit-stand work. We can also do each of the manual materials handling tasks that would be associated with the Snook and Ciriello Liberty Mutual manual materials handling equations. And so if you're going to use this module, those tasks need to conform to the limitations of the Liberty Mutual equations, meaning, for example, with lifts and pushes, mostly in the sagittal plane, done with 2 hands. And for more information, you can look at the manual. You can look at lifting tasks if somebody is, let's say, very asymmetrical, but we can invoke the Liberty Mutual manual materials handling equation. So we're essentially just looking at the postures associated with those tasks. And so in that case, you would do a standing static exertion. But if it is a standard lifting task in the sagittal plane, or somebody's carrying a load in the sagittal plane with 2 hands, then you can invoke these different modules. But we're going to use just the sample task that's in the manual. And so I'm going to set this to standing static exertion. If you pick the lifting load or lowering load, you're going to have to indicate whether you're assessing the postures when the hands are at the bottom of that lift, or the postures when the loads are at the top of the lift. So for example, during a lift, the bottom would be the origin and the top would be the destination. For a lower, the top would be the origin and the bottom would be the destination. And right now in Works, you have to tell it one or the other. We recommend when you do lifting or lowering loads that you do both. And we've set up a template in Excel where you can copy the results from the summary in the report for the bottom and for the top, and it will combine the two to determine where the highest peak occurred. Either, for example, was the compression highest at the bottom or at the top, and what the average load was throughout the lift for the fatigue analyses. And that is explained in another tutorial video that you can take a look at. But for right now, we're just going to look at a static standing task. So the frequency is done in efforts per day. Be careful that you don't put in efforts per minute. We're looking at things averaged across a whole day. So it doesn't matter if you did 50 lifts in the first 10 minutes and then did nothing the rest of the day, or if you spread that out over the day. Of course, it does matter, but all of the tools are insensitive to that. We don't really have a great way to account for the timing, at least not within Works right now. And you won't find that in any other tools as well. So we typically consider 1 per minute to be 420 per day, because in a normal 8-hour workday, you would probably have 2 15-minute breaks and a 30-minute lunch. So you would work for 7 hours, which converts to 420 minutes in a day. So let's assume for this task they do it once per minute. So that would be 420 times per day, or efforts per day. The effective duration is how long the peak would be experienced. And there is some explanations of that in detail in the appendix in the user manual. But let's just assume this particular effort is done for 1 second. If you were to pick a pushing task, you would need to indicate, are they pushing at 5 meters? Are they pushing at 10 meters? But in this case, that's irrelevant, so that gets grayed out. As well, if you were to pick a sit-stand task, you would need to tell it how high the hips are. So how high is the sit-stand? And so that becomes relevant. But again, we're just going to do a standing static exertion here. Okay, so let's go on to the next one. This is the barriers, and barriers really should be considered, not necessarily we need to completely replicate the physical environment, but they do represent things that would prevent certain postures. So if you're strategic about where you place 1 or 2 barriers, you can pretty much replicate most environments. For example, if you're in an automotive task and you have to lean over the fender of a vehicle, you could put a rectangle in front of the pelvis to prevent the person from leaning into the vehicle itself. Or if the hand has to go under something, you could put an object above that. Again, not necessarily a perfect representation of the physical environment, which could be very complex, but we found even in very complex environments with 1 or 2 strategically placed barriers, we can force the mannequin to avoid postures that would not be possible. And so in this particular example, we're going to have 2 barriers. So I'm going to say the first one. The first one we're going to say has a depth of 60 centimeters, so 0.6 meters. So you can see that's the depth there. We're going to say that the top edge is at 0.7 meters. And the bottom edge is going to be at 0. And you'll get some warnings. Let's say if for some reason the top edge is lower than the bottom edge, it'll just flag that for you. But as you progress through, you probably will fix that up. We're going to say that this edge goes negative 0.5 meters to the left. So you can see it now going to the left. So this is the depth of 60 centimeters from above. Here's the 60 centimeters forward. You can see the top edge is at 70 centimeters or 0.7 meters, and the bottom edge is on the bottom. And then here's the midline. The left edge is negative 50 centimeters to the left and positive 50 centimeters to the right. So now we've created this first barrier, and we're going to put another one in. So there's a vertical bar. There's some default values just so you can see graphically what things. This is indicating that it's a 0.1 depth, and it's got a top edge of 1.8 and a bottom edge of 0.8. So it gives you some frame of reference when you're putting this in. We're going to offset this 0.5 meters forward. So this now becomes our 0 point in terms of anterior location, and this edge is going to get put 50 centimeters forward, or 0.5 meters. And so the depth we're going to set at 0.1. We're going to put the top edge at 1.6 meters high. We're going to put the bottom edge at 0.7 meters, so it just is right on the top of this. And then we're going to have this go from 0.4 to 0.5. So you can see that it's 0.4 meters over and 0.5 meters over. So it's just in this back corner. And so you've got a frame of reference on this to see that you're more or less putting the barrier where you'd like it to be. And you can play around with that. If you save the report and the postures don't look right, you can read the report back in and tweak some of these. So now I've got a barrier that's going to potentially limit some of the postures. Later on, I'll be asked, is this something that the person could lean on? Because if they can lean on it, then that's going to eliminate balance or stability as a constraint to posture. So for example, if the person needed to lean out to this box, they might not be able to do it without leaning. And if you say that they can't lean on the barrier, then it may say there are no feasible postures. If you say that they can, then we'll remove the constraint where the center of gravity needs to be under the foot, because this barrier will prevent them from falling over. And then there may be feasible postures that it could find. So let's move on now to the next. This is going to be the hand contact locations, and you'll get a graphical representation of that. And so for right now, again, because we have a barrier, all of the anterior coordinates will be with respect to this, because we're going to assume the person's going to get as close to this, either their toes are going to hit it, or their knees, or their chest if it's high enough. So all anterior coordinates will be with respect to the barrier if one exists, and they'll all be with respect to the ankle if no barrier exists. So in this case, we're going to say, and again, left is in blue, is in orange. So we're going to say that the load is 1.5 centimeters anterior, and you can see that a box with the force vector is shown up, and we'll continue to refine that. We'll say it's 0.8 in the air, and let's say that it's minus 0.25 to the left. So here you can see that it is 15 centimeters forward of the box edge. It's, with respect to the ground always, it's 80 centimeters or 0.8 meters. And with respect to the midline, it's left negative. So negative is left. You can see that here. And negative 0.25 meters. So now let's build up the, and now you can turn off the left arm or turn off the right arm. So if I turn off the left arm, it doesn't require any inputs, and it'll make some assumptions about the posture. So let's put the left hand. It's now going to be 0.35 meters forward. We're going to put it at a higher height of 1.2 meters. So you can see it's now 1.2 meters off the ground. And we're going to put it to the right 30 centimeters, so positive 0.3. So now we have the hand locations. Here are the force vectors. It's assuming the force is up because we haven't gotten to define those yet. But you have a visual representation from behind, from above, and from the side of what that looks like. Now we can go to the effort directions, and this can be done. You can either put in the actual force in each direction, or you can just give the relative component. So for example, right now it's assuming that the force is 1 part up and 0 parts, or 1 part forward and 0 parts up and 0 parts to the right. So we're going to put this as 1 part forward. We're going to put this as 1 part up, and you can see the force is equal parts up and forward for the blue, which is the left, and we're going to say that it's 0 to the right or left. For the right arm, we're going to say that it's 0 parts forward or backward. We're going to say that it's 0 parts up or down, and it's going to be minus 1 to the left. And so you can put in these. If you know the actual vector, then you can put that in. If you know it's 22 newtons forward and 57 newtons up and 37 newtons to the right, then you can enter those values, and then it will calculate the unit vector. So it's equal parts forward and up, so the unit vector would be 0.707 and 0.707, because this squared plus this squared would add up to 1. That's why it's called a unit vector. In this case, because it's all in the left direction, the unit vector is -1. So if you know the unit vectors, you can enter those as well. In this case, we're going to assume the force is 35 newtons for the left hand and 30 newtons for the right hand. And that will affect the length of this vector. So now we move on to probably the most difficult part. And we spent a lot of time on this, did some studies with Fanshawe College to try to come up with a good user way to do this. but it does take a minute or two to try it out. But the first thing is, if you've used Handpack, this has all of the different hand grips associated with Handpack. Power grip, pushes with lateral pinches, pulp pinches, pushes with the tip of the index finger, the pad of the index finger, the tips of two fingers, pushes along a cylinder with an oblique grasp or a medial grasp, so you can see what that looks like if you choose that. Pulls with different pinches. So anything that you may have seen already in the Handpack software would be here. In this case, we're going to say that they're pushing along a cylinder. Let's say like a hose push. So push along a cylinder with an oblique grasp. So there you can see they're pushing here. And let's say that they're also doing the same thing with the other hand. So they're pushing along a cylinder. Okay, so probably the most difficult part to conceptualize is we now need to think about, if you think of a line going along your knuckles from the knuckle of your pinky to the knuckle of your index finger, the direction of your thumb, if you're sticking your thumb out, we need to define what that direction is. For example, if you had your hand straight out in front of you and the palm's facing down, your left knuckle would be facing to the right, and your right knuckle would be facing to the left. And so we can see a visual representation of that here. So in this particular case, we're going to assume that the left hand, from the side, the thumb is pointing up and forward, or the knuckles are pointing up and forward. And then we'll have to define the palms as well. Let's say that for the right hand, the knuckle is pointing directly from the left. So again, if you stuck your hand straight out in front with your palms down and you look from above, you would see this. You would see that the thumb is going in this direction. And then we need to tell it what direction the palms are going. For example, in this particular case, we're going to assume that the knuckle so this is for the left hand. So imagine you have your knuckle, you're in a handshake position, but then you tilt your hand down so that the thumb is going up and forward. And you could imagine that your palm would be facing to the right side. In the other case, if you had your hand out in front of you with the knuckle going to the left, you could imagine that your palm would be down. And so you can see that from the side, you can see it going up and forward. And from above, you can see the palm is facing to the right. And then for this one, you've got the knuckle going to the left, and from behind, you can see the palm is facing down. So that seems a little confusing the first time you see it, but people usually get that sorted out fairly quickly. Because they're pushing on a cylinder, whatever options would be in Handpack are in the software. So when the span is relevant, you would need to enter the span. So let's just assume that's 30 millimeters. For some of the pushes with the fingertips, you might need to know whether there's a glove. Because you're pushing on a cylinder, is it a rubber hose or is it a plastic wire harness? You need to indicate that. So we'll just assume that it's a rubber hose at this point. So that part probably will take a little bit of practice, but people usually pick that up fairly quickly. If, for example, this person, you had told it the palm was upwards, which would almost be impossible because your fingers would have to be pointing back at your body, the software will show you that posture and indicate what the likely issue is, because it won't be able to find a feasible solution. So you'll get some feedback, and usually people pick that up fairly quickly. Now, the final thing here is a few other analysis settings. We want to know where the person is looking. So they could be looking straight ahead along the horizon. They could be looking at the midpoint between the hands. You could pick a spot out in the distance that they're looking at, or the neck could just be in the neutral position. But we'll have them looking at the hands in this case. The above shoulder correction, we're going to turn that on. That, as you can read in the user manual, is based on publication I did with David Rempel in 2022. That has since become an ACJH TLV. So you may choose to, that basically looks at the impingements that could be caused on the tendons if you rotate the upper arm up so that you're grabbing things above the shoulder. I've recently developed a cumulative compression calculation, so you can turn that on, and that may be a limiting factor. You may decide, for example, if some task like a lift is being done just purely in the sagittal plane, you may not want Works to find all kinds of lateral bend and twist postures. That might be feasible, but it might be unlikely. And so you can limit the trunk to just purely being in the sagittal plane, but this is a more asymmetrical task, so we won't do that. We'll say that box, the lower extremities can lean against this barrier. Of course, if it was a cardboard box, it would fall forward if you leaned on it, so that might not be possible. But let's say this is a rigid, heavy table that you can lean against. And also, if you're doing work way up above your head, it's not likely, even though you might be able to extend your arms more and bend your knees, it's not likely you're going to do that. So you can tell it to just analyze tasks with straight legs, but in this case, we're not just going to have it do the straight leg tasks. And so we've got everything on here. I can give it a name, and this will actually go in the summary table. You can always change that later, and this will be the default file name when you do the analysis. We've got everything in here, and we're ready now to do the analysis. And so I am going to click on Calculate Outputs. You'll see that there's a processing stages that happen. This will take maybe 50 seconds or a minute. There'll be a lot of postures with this particular task. You do get feedback along the way of how far along it is on the analysis, but at this point we'll pick up once it's done the full calculations. Okay, so this has now completed the analysis. This would be one of the analyses that had one of the most postures I've seen. It's over 100,000, about 104,000 postures. So that took about 1.9 minutes. Of course, you didn't have to do any posturing there for that, but each analysis tool is run on each of those 104,000 postures. So now we have our results. We can see a map here showing the postures. We've selected postures in around the 25th percentile risk, and you can see that most of them are acceptable, those shown in green. The criterion percentile is shown with more of a full body and head, and then some stick figures are shown around it. Those that were acceptable are in green. It seems that because the overall risk score is 0.7, that 70% of the postures had a DCR, an overall DCR less than 1. And we set our threshold of having at least 25% of those to be considered acceptable. And there's lots of data that can be exported into a report, and I'll show you that in a second. But as soon as the run is done, you can see the body map. In this particular case, it appears that the left arm is maybe the limiting factor. And then there's a ranking here, which assures us that the left arm is the one that has the highest. So you see the overall and then a ranking from highest to lowest, so you don't have to go hunt through this. So we've got all of our results. I can say export. So I am going to just save that to sample task 2 because I've already saved this earlier. And now everything has been saved. I can hit the back button here and it'll bring all of the inputs back to populate the input. And if you want to tweak right now, you can do that. So you could go in and change the force direction, or maybe you had the hand orientation in the wrong direction. Or I'm just going to reset everything here. And if I want, I can go into this load inputs. I can read in the file that I just created, and it will repopulate. So you can come back and do this later if you like, and then tweak the analysis. And once you do that, it's probably just good to remember to change the file name or the task name here, or at least remember to change it as a different file name once you go to save the file. So this is just a bit of a tour of the interface. There's a lot more information explaining this in the user manual, but this is a quick how-to guide to get started if you're just using Works for the first time.